So let's carry on with note on work. So what I did yesterday is I drew a little picture here just to, did I only make it appear later? Where is it? There. We were discussing this question, and I drew a picture here just to make the question a little bit more obvious, okay? So you've got a rocket going up. It's propelled with a constant force of 680 newtons. The force that it's been propelled up with is bigger than the force of gravity, right? We know that because the you can calculate both of them. You told the 680 newtons, and you know it's a 40 kilogram rocket, so the force of gravity is only 300 and something newtons. So if you've got 600 newtons going up and only 300 and something newtons coming down, then the force going up is bigger than the force going down, so it's going to have a net force going up. We all agree with that. So yesterday we did a little bit of this. We got to I think we did that one. The work done on an object by the gravitational force. And that was minus 31,360 joules. So the next question we had to do was the network on the object. I think we did that just before we left. And to get the network, you just add up the work of all the forces on the object. This object only got 2 forces, so you're adding up the work done by the force F, and you're adding up the work done by gravity. And because that one's negative, it reduces the amount of work, and so you'll end up with 23,040 joules. W net is equal to, there isn't a formula for, well, there is a formula for W net, but there's 2 different ways to work it out. Nick, are you doing your vertical motion worksheet? Because if you are, you're being silly. Because this stuff's not easy and you're going to get left behind. So this formula, gentlemen, they're not going to give you. W net is equal to WF plus WG. All that is saying the network is equal to the sum of all the works. So if there's one object and it's got 6 different forces, and each different force is doing a different amount of work, to find the network, you just add up all those works. But you've got to remember, if one is negative, you've got to bring this negative sign with it. Yes. On this one, not on this one. There's not on this one. You're on the wrong example. Yeah. Where is that? It might be the next one. Ignore the friction then, because this one I'm doing has got no friction, so just ignore it. Yeah. So, gain in potential energy. Gain in potential energy you can work out just using the potential energy formula. It's mgh. Right? Now, there's something important here that you need to note. So the mgh, the object was 40 kilograms, g is 9.8, the height was lifted 80 meters. That gives you 31,360 joules, which is a number that you've just seen. Now, can you see, and you need to take note of the fact that the gain in potential energy is the negative of the work done on the object by gravitational force. The work done by gravity is the negative of the gain in potential energy of the object, if it's going up. Because, and that's perfectly logical, because if you're lifting something up, it's gaining potential energy, but you have to fight against gravity to do that. Gravity is fighting you all the way. So the work done by gravity is negative, but you are giving the object potential energy. And those two will be equal, but the one will be negative. Happy? U is the symbol for potential energy. One of the symbols. You can use EP or you can use U. Right. So that's important to note. Okay? Maybe make a note of it somewhere, scribble it down. The work done by gravity is equal to the gain, is equal to the negative of the gain in potential energy. So what's the gain in kinetic energy? You can use the work energy theorem. The net work is equal to the change in kinetic energy. Now we've already worked out the network in B, so that is your gain in kinetic energy. That's the work energy theorem. It was on the previous page. Yeah, the work energy theorem. And it turns out to be very useful. You can do almost all your work energy questions by just applying that theorem. Okay. And then the kind of thing they often ask you is the speed, the final velocity of the rocket. So this rocket was propelled from the Earth by a 680 Newton force for 80 meters from the surface of the Earth. And the question they ask you at the end is, what speed does it get to? So once you've got the gain in kinetic energy, you can just use that to work out the speed. So K is for kinetic energy, there's a number of symbols. You can use EK or you can just use capital K. It's the same as potential. You can use EP or capital U. Yeah, that's from the previous slide. Remember we did this work energy theorem? Delta EK is equal to net work done. Right. Half mv squared. Yeah. So the gain in kinetic energy, well, the change in kinetic energy was, it was initially 0. So the change in kinetic energy is final minus initial, but since the initial was 0, it's just equal to the final. So EK, the change in kinetic energy was 23,040 joules. You just work that out, half mv squared, so you can work out your velocity. 33.9 meters per second.
So the answers below the difference. This one is friction. That one has friction.
Okay, so ignore the friction. I'm sorry about that. I didn't realize that I put in friction as a second example. We will do some examples with friction. Louis, that's strike 2. Sorry? Tape their masks to their nose. Tape their masks to their nose. Okay, so look, we're going to work through a number of examples like this. We're not going to take you through step by step, just because doing these questions, once you get into that too. 2, 2, 2. A lot of these questions, guys, once you get used to the method, they're actually very similar. Although all the questions are very different, the method that you use to solve the problems are very similar. Okay? There's a number of different routes you can use, but you're using the same thing. So we'll go through a couple of examples, and you'll see they should become easier.
We're not going to go back and go through like the pendulum and that.
Comes towards the end. Comes towards the end. I think the slides just go into a slightly different order. So let's have a look. You've got an object lifted by a force at a constant velocity. Calculate the work done by the force F and the work done by gravity and the net work. So do you want to try this yourself? An object is lifted by a force at a constant velocity. Okay, it's a 2 kilogram object. It's lifted for a height of 3 meters. So the drawing is giving you the scenario.
This is slightly different. This is accelerated.
Okay, cross-eyed accelerated. We're going to work with this. I don't know what happened there. I'm sorry. There's another one that's accelerated. So on the next page, there's one that's accelerated. Okay. So how are you going to work? So the first question here is calculate the work done by the force. Now, have I told you how big the force is? So how are you going to do it? Constant velocity tells you what? The net force is 0. So the force lifting it, what do you know about it? Equal to the force of gravity. And since you know the mass, so you can go for it. So I've given you the formula for the work done by force. F is F delta x cos theta. You now know the size of the force F. You know delta x, it's been lifted for a height of 3 meters. And you should know cos theta. So you can work out the work done by force F. Then I'm asking you the work done by the force of gravity. No, you don't have to do it first. You can do those in any order. Yes, 100%. So has anybody got a number for me? How much? 38,8. 58,8. All happy? Now it's asking you to work out the work done by gravity. Now, it's important, yeah, to listen to the wording. The work done by gravity is not the same as the work done against gravity. Okay? I'm asking you to work out the work done by gravity. What's your formula? WG is equal to what F? FG. Delta X cos theta.
What's the difference between WF and WF?
So WF is the work done by the force F. WG is the work done by gravity. Again? So you get the negative of the previous one, minus 58. So then I've asked you to work out the network. Network's going to be 0. Why? We should have known that from the start. Why is the network going to be 0? Constant velocity, therefore? Therefore, 0 work is done because the network that's done is equal to the change in kinetic energy. And if the velocity is constant, there's no change in velocity, so there's no change in kinetic energy. See?
So if the ball reaches terminal velocity,
yes,
there's no work done.
No network being done. There is work being done on it by gravity, and there is work being done on it by friction, but those two are equal and opposite. Not, well, yeah, equal and opposite. So there's no network. The term network, I actually struggle with, I actually don't like it because it kind of gives you I think it gives you a slightly wrong impression. You kind of think, if you think the net result, well, if you think of net result, then maybe it is okay. We used to, from vectors, we did resultant vectors. I walk there, then I walk a little bit back. What's my resultant displacement? It's the one minus the other, yeah? But when I think of net, I think of the sum total of everything that's been done. So if I think of network, then I think of, if there's work being done by friction and by gravity, then I think the network is adding those two together, not the difference between them. But this definition for network is the work, all the sum of all the work's been done. So we've got those two, we add them up to get 0 joule. Okay? Although there's lots of work being done, the net work is 0. Happy? There's work being done upwards and downwards. The upwards work has been done by friction, the downwards work has been done by gravity. In this example, it's exactly opposite way around. So, applying the work energy theorem to this, you've got delta EK is equal to the net work done, and that's got to be 0 because it's constant velocity. Anytime there's constant velocity, the net work done is 0. And so therefore the work done by friction plus the work done by gravity is equal to 0. So the work done by friction is equal to the negative of the work of gravity. Now, I haven't said it. Every time there's constant velocity, the net work being done is 0. Now, I haven't worked it out. I didn't point it out at this point, but the net force has to be 0 as well. Because the net force, we said the force of gravity down is a certain amount. The force being used to lift it was the same amount. So what's the net force? 0. So in all these situations where the net work is 0, the net force will also be 0. Well, remember, if you lift an object at constant velocity, the only force you need is the force that's equal to its weight. You would have needed a slightly bigger force for a fraction of a second just to accelerate it. But then you can drop the force back to the same as this. Now it's moving up already. If the forces are balanced, it'll carry on moving with constant velocity forever. So the smallest force you need to lift something is equal to its weight. Actually. So, yes, I'm listening, Jonty.
Is work done at like one instantaneous moment?
No. We're talking about the total work done over the whole 3 meters.
Okay.
Question? Yes. So we're going to do that now. Okay, here's another example. Try this one. Now the object is accelerated from rest vertically by a 40 Newton force over a distance of 3 meters. It's still 2 kilogram object. I want you to work out the same values. The work done by the force, the work done by against gravity, and then I want you to work out the net work. Try it, I'll give you a few minutes.
Sir?
Yeah, I'm listening.
What confuses me is that, okay, so what if there's an object which is out of space and it has a force done on, like acted on it for like half a second, like a 5 Newton force or whatever.
Yeah.
It accelerates and then it stops and it will carry on going forever because there's no like friction or anything.
Yes.
And like Newton's second law or whatever.
Yeah.
So then is the work done not like infinity? Because the distance will just keep on going.
Well, remember, at what's happening at the time, as soon as it hits constant velocity, there's no net work being done. And in fact, an object in space, moving at constant velocity, it's actually got no force on it. Can I put it up? Yes? Right, so work done by the force F. And it's dead easy. Work done by F delta x cos theta. You just take the force you're considering. So we know the force up is 40. We know delta x is 3. And you know that in that case, the force and the displacement in the same direction. So 120 joules. If you got that, stick your hand up. Cool. So now, what's the work done by gravity? Well, gravity in this case, so work done by gravity, again, your formula is just Wg is equal to Fg delta x cos theta. Force of gravity we know is going to be 2 times 9.8. We know displacement is 3. But now the gravity is down and it's moving up, so it's 180 degrees. That's where your minus comes from. If you put the 9.8 in as a minus, you're going to get 2 minuses, and it's going to cancel out. Yes?
So work done against gravity equal to work done by gravity?
No. Equal, but one will be negative, one will be positive. No. I'll tell you why in a minute. So here the work done by gravity is 58.8 joules. Now, this is the work, flip. I froze the screen. Let's unfreeze it. Now, have a look at this. The 120 joules of work that has been done by F, 58.8 of those joules are being used to overcome gravity. Okay. And the excess will be used to accelerate it.
Do you have to take plus 1?
Yes. Yes. There's a mark for that. That's where you get your -1 from. All right? So what's the network going to be? Is the network going to be 0? No. So now work energy theorem, we know that network is equal to change in kinetic energy, but we know the network is also equal to the sum of all the works. So now you can just add up the two values that you've worked out, and the net work done will be the 120 minus the 58.8, so 61.2 joules. That's the work that's going to accelerate the object, which is causing the change in kinetic energy. And that's why the change in kinetic energy is equal to the net work done. Did you have a question? Okay. Okay, change it. Make it work done by gravity. The work done against gravity is different. The work done against gravity is the work done by the force that's working against gravity. So it's actually a bit of the force that's being applied, some of it's being used to overcome gravity. So that's the negative of the work done by gravity. Yeah. So it's important when you're talking about the work done, you need to specify what force you're talking about. Okay, so work done by F and work done by G is equal to 61.2. And now let's work out the net force. In this case, the net force is not zero. The force up is bigger than the gravitational force. So you can work that out. You can say the net force is 20.4 newtons. That's your work energy theorem. I could have asked you to work out the speed again, in which case you would have just done this. But that's not massively important. That's just a little application of the same thing. Nick, you seem to be sending a message. Now, there's another way to work out the network. There's another way to work out the network. Okay, listen, I'm hassling by the UX today. I don't like the attitude I'm getting. Somebody's out of line and you start laughing at him. That's not acceptable. And then it just goes downhill from there. So there's another way to work out the network. You can do it like we've done it here by adding up the works that you've already calculated, or you can do it using the net force. So here I've done it for you. Using the net force, you take the net force, which is 40 minus the 2 times 9.8, use that times the displacement, and obviously the net force is up and the displacement is up, so it's cos of naught. And that gives you the network, and you can see that network is exactly equal to the network we got by adding up the two values of work that we had calculated. So I did it there both ways. It doesn't matter which method you use, both ones you'll get the same answer. I actually think using the net force is easier, because you just add up forces like we did in Newton and then use that to work out the total work, but it's up to you. Yes, question?
So F net, why is it 2 times minus 9.8?
F net, here, where be? Because that's mg. Yeah, that's mg. That's multiplication sign. Yeah, I'm just using it because they're not just dropping it into my spreadsheet. All right. So you should be starting to get a little bit of hang of the method. Okay. This is the kind of example you're going to get. You're going to get an object which is undergoing some kind of motion. It's got a number of forces on it, and we're going to ask you to work out the work done by this force, the work done by that force, the net work. We might ask you to work out the velocity. We could even ask you to work out the acceleration. Yes. Yeah. So we're not going to ask you Newton. We're not going to say, quote Newton's first law and all that, but we expect you to know it because you need it to work out this kind of thing.
But we don't. Is friction included in this section?
Yes. Friction? Let's try this one. You remember all the stuff on components? How much time we got? 5 minutes. 5 minutes. Okay. I'll let you work on your worksheets for 5 minutes. We'll leave it there.